All right, hi again, everybody. We're gonna continue where we left off on section 4.2. We're almost done with it, so just a few more examples and properties. But just to refresh, I guess, what we were doing is remember the idea was that if we wanted the area underneath the curve from the point A to B, if we have a function, say it looks like this, and we want the area under the curve, or above the curve if it's negative, meaning if we want to find the area like this area right here, right, we would take these positive areas and subtract it from this one. That would give the net area. So this was the whole goal, is to find this net area. The way we did it is we used rectangles, right? We used the rectangles to approximate the area, and those were the Riemann sums. So remember, we had the Riemann sums, which was basically, again, this was the base, the delta x was how wide our rectangle was, and we multiplied it by the sum of the heights, where x sub I, like x1, x2, x3, this is just some set of sample points. So again, if we write this out in full detail, this is what we get. So each delta x times one of these was the area of one of the rectangles. And then we said, if you want to get a perfect answer as opposed to an approximate answer, we're going to let the number of rectangles become infinite. So what happened is this delta x got changed into a dx. So that's the change we see here. Delta x went to dx. And when we also replaced this sigma, this is the Greek letter sigma right here, the sigma turned into this elongated S symbol, which is just called the integral sign, or an integral symbol. It's a S, and the S stands for sum, you know. It's supposed to represent sum, the idea that you are doing a sum. So these two changes overall gave us a new notation. And so this is the perfect area. This is the actual area underneath the curve, as we wrote it like this. The integral from, read again, the integral from a to b of f of x. Some people say of f of x dx. You don't have to say the dx if you don't want to. But this is the perfect area. So this is approximate area. This is the actual area, perfect actual area. All right, so that's all, well and established, so we know what this means. It looks very daunting at first, but that's all it means. It's just the area under the curve. And so we saw some properties of this guy. For example, we saw that if you try and find the area under the curve of two functions added to each other or subtracted to each other, you could effectively just find each of the areas separately and then add or subtract them. Sorry, got it right. Okay. So that was one property. Another note is that there's nothing sacred about calling this x and x, as long as these two are the same variable. So this is the same thing as, if we replace these guys with a t. We're just used to calling the variable on the horizontal axis, or the independent variable, we usually call it x. But t is just fine, like in physics, t represents time, so that's normally the independent variable. This could be an r, a q, it doesn't matter. So that's just a nice note. The variable doesn't matter. And some people go as far as to say that this variable is called a dummy variable. I'm not sure where the idea comes from, but I guess it just kind of means like, it doesn't really matter. It's there and it's irrelevant. It could get used, it's going to get used, and it's going to go away. So that's just a quick note, is that the choice of, t, x, whatever, it doesn't matter. Okay? And then let's do one quick example before jumping into the last set of properties of the definite integral. So then here's another example. So suppose we know this. So we have some function where the area from 0 to 10 is 17. And we have another function where the area from 0 to 8, it's the same function. So same function, both are f of x, is 12. So we know this. So suppose this is true. So now we ask the question, what is just the area from 8 to 10? What does that equal? Okay, so maybe just this. What is this guy? Okay, so picturesquely, let's draw a picture of this to help us understand what's going on. So we have a function. Here's 0. Here's, let's say, 8. And here's 10. And, we have some function. I don't know what it looks like, but let's just say it looks like this. Okay? And then, so what we know is that from 0 to 10, so from 0 to 10, all of this here is 17. The area here is 17. But then from 0 to 8, if we go just to 8, this area here in green, it overlaps with the blue a little bit. This is 12. Okay, so the area that we're really just trying to find is the area from 8 to 10, right? That's what this is it. That's what we're trying to find. So what would you do? You would just subtract the whole area up to 10 from the area up to 8. So this is the area that we're really interested in. That's actually what we want. Let me put it in red. So this is the desired area. Let me get rid of this now too. So this right here, this is the desired area. And being able to make pictures out of these scenarios is really good, because you will understand this on a much better level when you see pictures of it. So this is literally going to be the area up to 10 minus the area up to 8. Remember, this was 17 and this is 12. So 17 minus 12, so it's just 5. So the area that we're looking for is just 5, this area right here. So again, this is a nice example of how this concept of the definite integral or the integral is very geometrical. There's a lot of pictures that you can draw here. Okay, this simmer in. Okay, and then last but not least, we can now get to the final set of properties, which I'll restart, I guess, because these are the comparison properties. So comparison property 1. I'll restart the numbering. So this says if your function if the outputs of your function are always positive or 0 on the interval AB, then your area, right? If your function never goes below the x-axis, if it's never negative, what should your area be? Well, it should definitely always be either 0 or some positive number. So that's the first comparison property. Like, for example, this means your function never does this. It never goes below the x-axis. It never gets negative values. So if it never has any negative values, then it looks like this. You know, it's just chilling above the x-axis. So if you calculate the area from A to B, this is definitely a positive, or it could be 0, right? If your function is just flat at 0, if it's the 0 function, meaning f of x literally equals 0, then your area will be 0. But, you know, besides that, this is all that can happen. So, not too bad. Okay. Then there's also comparison property 2. And then this says so this means that your function is always on top of the other one. The output of this function is always larger than the output of this one, even in the case of negative. So like, for example, if this was -5, this would be -2. So it's still above g of x. And I'll draw a graph just to double check if that makes sure. But if your function is always on top of the other one, it would make sense that the area underneath it, or the net area, should be larger as well. You know, we have this, so let's say this is f. Then if g looks like this, so for positive values it's underneath, right? And then for negative values it has to be more negative as well. So let's say it looks like this. This is g of x. Well, then you could see that, you know, if you just focus on this little bit right here, even, the area underneath this guy, the red one, is more than the area underneath the green one. It's the area underneath the green one plus some little extra area. And that's going to apply for each little piece here. So you can see why this property is true. And again, these seem very random, but they come very, very handy in many scenarios. And then comparison property 3. Okay, so this seems like a mouthful. Let's definitely unpack what this is saying. So what this is saying is that your function f of x is always larger than some number m, but always smaller than this bigger number, capital M. Meaning it's sandwiched between those two. The output can be no lower than this and no bigger than that. So for example, if you think about, let's say f of x is x cubed on negative 1 to 2. Well, this function here, at negative 1, it's negative 1 down. At 0, it's 0. At 1, it's at 1. And then at 2, it jumps up all the way to 8. So it looks like this. Okay. Roughly, not the best, but roughly it looks like that. Now, on this interval, negative 1 to 2, m would be this one, small m. So this is lowercase m. So this is m. Because see, the output of our function can get no lower than negative 1. And then this 8, this is capital M. Because the output of our function can get no larger than this. So that's what this means. And then all this is saying is that the area underneath the curve here can't be any bigger than the area underneath the curve if we just consider the function to be constant at the lower value or the upper value. So what do I mean by that? So if instead on this interval we said the function the whole time is like 8. The whole time the function is 8. It doesn't go like this. It's just always 8. It's just always constant at 8. Then the area underneath the curve here, the area under this guy, which is, you know, the height of this is m, which in this case is 8, and the width is b minus a. So the area underneath this is capital M times b minus a. So it's saying the area underneath this guy is always going to be larger than the actual area underneath the curve, or the net area. Because see, this is the net area right here. See, this pales in comparison to this large rectangular area, and you even take a little bit away because it's negative. And then you can do the same thing with small m. If you think about the function always being constant at small m, like this, then this red rectangle here, this area here, is way, way more negative than this already. And then, you know, this net area is positive, and this is a very negative number. So again, the actual area underneath the curve will be larger than the area created by the smaller limit. So that's all this is saying. And again, this is good because it can help you control the size of an integral if you need. Some of these, again, are more used in proofs and things like that, but they will probably come up somewhere or later in our adventure into integral calculus. Okay. So yeah, I think that's good for now. We can definitely move on to the next section. So that's all the properties of the definite integral and things like that. And now we have come to the point where we can start talking about, you know, what I promised is the big shot theorem of this entire subject, core subject. It reoccurs again in calculus 4 and 3, you know, like this same concept in higher dimensions, but it keeps happening. So this is the fundamental theorem of calculus. Fundamental theorem of calculus. Very, very, very important theorem. So to get started, we need to understand how to interpret what this means. So suppose we define this function g of x to be this. define this guy to be that way. And so now you might be like, hey, why didn't you use an x here? Why'd you use a t? Well, it really doesn't matter, but just to be, you know, fully like clear, there's an x here. So we want to avoid using an x in this case. And again, remember this choice here doesn't matter. So we're just going to use t instead. Anything but x. This could have been q, r, s. Anything you want. But we want to figure out what the heck this means. Now, if you think about what a function is once I give you a number x, you should be able to give me an output, right? So for example, g of 1 would be the integral from a to 1 of f of t dt. G of 2 would be the integral from a to 2 f of t dt. And let's just suppose, you know, now we kind of like fix some value for a. Let's suppose that we just say a is 0, whatever. What is this function telling us then? Well, the function is kind of just gradually, is telling us the area from a or 0. So in general, this is like a, all the way up to some point x. So let's say you have a function f that looks like this. Then this is your function f of x. Then the area from a up to the point x, whatever this area is, this is what g of x is. That's what the output is. So for example, when g was 1, the area from 0 to 1, that would be the output at 1. And then if x was 2, so let's say 1 maybe. I say 1 here. So this would be g of 1. And then if you say 2 here, so we have 2, then this area all the way, and then this one also, all of this here, all of that would be g of 2. So that's the output of the function g, right? I gave you the number 2, you stuck that into the function g, and your output is whatever this area is. It's again just some number, right? So this is really a function. It truly is a function. And we're going to be exploring this function in great detail because we need to see how it relates to the fundamental theorem of calculus. Okay? So let's take this again. And let's do a concrete example now. So let's define g of x to actually be the integral from 0 to x. And then let's say the function f of t looks like this. So, oh, only 0 value, okay. So then, maybe just to save space. So yeah, we're going from 0, so let's say this is 1, 2, 3, 5, and then 6, okay? And then 2. So then between 0 and 1. So it's a straight line between 0 and 1. And then it flattens out between 1 and 2. Flattens out like this. And then between 2 and 3, it kind of takes like a dive like that. And then it hits some minimal value like this and comes up to 0. Okay, let's just say it looks like this. So this is our function f of t. So on the horizontal axis, we're putting t basically instead of x. Remember, it doesn't matter too much. Okay, So let's actually compute what g at each of the inputs would be. So what is g of 0? So g of 0 is the integral from 0 to 0 of this. And then what happens when we had the same limits of integration? This was one of the properties of the definite integral. This is just 0. Because what's the area underneath the curve from 0 to itself? You know, you haven't moved to the right or left at all. There's no width. The width is 0, so you have no area. Okay? Then what's g of 1? Well, it's the integral from 0 to 1 of this guy. Okay, and now if you think about it, you can actually find this very nicely. This is the area of this triangle here. So what is the area of this triangle? Well, it's 1/2 times the base, which is 1, times the height, which is 2. So we just get 1. Okay? And then what is g of 2? Okay. What is g of 2? So g of 2 is going to be this old area plus this new area that we get here. So it's the old area, 1 plus the area of this rectangle, which the base has length 1 and the height has length 2. So it's 1 times 2, so just 2, which is 3. Okay? And then g of 3, what is g of 3? You might have caught on to the trend here. Okay? So g of 3 is going to be, again, the old area. So 3 plus this new area here, which maybe I'll put like squiggly lines or something. Okay, it's kind of hard to say exactly what the area is, but comparing this with the guy right next to it, you know, this is just an estimate. There's no like perfectly right answer. It's like not quite half of this, right? Like if you cut this guy off following the same trajectory as the curve here, you would get a little less than like half of it. So maybe it's like, it's about half of what you get there. So, you know, it's up to you. This is up to your interpretation. But what the book says is approximately is that this will be 1.3. So they're saying it's like, you know, 1.3, sure. Maybe it's 1, maybe it's a little more. I don't know. Again, but just to stick with what the book has, so it's not confusing, this will be 4.3. So we're saying this area is like roughly a little larger than this like half of the area here. Okay, not too bad. And then let me kind of just collect these pieces of information so I free up some board space. So g of 0 was 0, g of 1 was 1, g of 2 is 3, and g of 3 is 4.3. Okay? And then let's do g of 4, which is the integral from 0 to 4 of f of t. Okay. And then now again, you have to do a little approximation. So we do another approximation. So like we said, it's the area up to this point. So it's the 4.3. But now we have some negative area. So we have this area. So we have to subtract this off. And again, you can kind of see that these two areas are roughly the same. That's the way the book interprets it. Again, it's all just guessing, so don't be like, oh, I got 1.2, not 1.3, or I got like 1.7 or something like that. It's not too big of a deal. So then again, if we subtract off the 1.3, the same area, this lands us back at 3. So this is 3. Okay, so G of 4 is 3. Then last but not least, G of 5 is going to be 3. You know, all of this, the net area up to this point, and then that. And again, you can see that this is pretty symmetric. So if this was, you know, if this had a net area negative 1.3, so should this one. At least that's the way I see it. And the book also sees it that way. So this will be 3 minus 1.3, which will just give us 1.7. Okay. So then last but not least, we have G of 5 is 1.7. G of 5. Okay. Now why did we go through all of this trouble? Well, let's graph this function now. Let's graph G of x. And we're going to graph it directly underneath this guy for a good reason. Try and keep it as close as possible. Okay. Now, let's see. So G of 0 is 0. Okay, not too bad. G of 1 is 1. Let me put this in black. Or maybe I'll have to put 1 here. 2, 3, 5. Okay. So that's, and then G of 1 is 1. G of 2 is 3. G of 3 is 4.3, so slightly above. And I'll keep repeating this. Okay, so we get this roughly. And then, so this is kind of what that looks like. So one immediate thing is, if you remember from Calc 1, anytime you have like a hill like this, right, that would mean that the slope of the tangent line is 0 here. Oh, and maybe let me label this. This is G of x in blue. This is G of x. So anytime you had a hill, the slope of your tangent line was 0. And now look, at 3, this has a value of 0. So what you can say is that G prime at 3 is the same thing as f of 3, which is 0. Interesting observation. The derivative of G is the same as the output of the function at the same point. Okay. And now, if you look between 1 and 2, this is roughly a line, right? If I draw the slope of a tangent line, it kind of looks the same. Like between this point, the tangent line looks like that, and then this point, the tangent line looks essentially the same too. Meaning that these numbers are all the same, the slopes. So what that means is for x between 1 and 2, g prime of x is equal to, and actually the slope is, in an ideal world, it would work out to be 2. It's the same value as this, how high the function goes. So g prime of x is 2, and that is again the same as f of, I don't want to write x, but like we said, the x, the t doesn't really matter, but this guy here, what we're saying is, for example, let's say g prime of 1 is the same as f of 1. So the derivative here, the slope of the tangent line here, is the same as the value there, which is 2. G prime of 1.5 is the same as f of 1.5, which is again 2. See, this guy never changes, and these slopes never change. Okay. And then another observation is, look, immediately after 3, what happens to the slopes of the tangent line? They all take on negative values. So these slopes are negative, and look, the output of the function becomes negative. And this is not a coincidence. None of this is a coincidence. So you would be very, it would not be too surprising to think that the derivative of this function is actually just f. Meaning, if we summarize this, very important, is that what we're saying is that g prime of x is equal to f of x. So the derivative of g is f. And then what was g? Well, g was this integral thing, right? So remember, how do you write derivative? Is you say, what we're saying is that the derivative of g, well, what was g? It was the integral from a to x, or 0 to x, of f of t dt is just f of x. That's what we're saying. Because this is g of x. So we're saying the derivative of g is f. And we saw that very clearly. We saw that the slope, the derivative of g here was 0, and that was the same value as f is 0. And then we saw that all these slopes, the derivative, the value of the slope was a constant 2, and that's the value of the function, is a constant at 2. And then whenever this became negative, the outputs of this guy became negative, the slopes. So the slope of this function, or the instantaneous rate of change, the derivative of this function, is just the same as the original function right here. And this observation is called the fundamental theorem of calculus part 1. That's a mouthful, so let me just write it down in all of its full glory. I mean, I would love to see the faces of the people who discovered this for the first time. It's like Sir Isaac Newton, his advisor Sir Isaac Barrow, some German mathematician, Gottfried Leibniz. These people did, they were probably shocked when they discovered all of this. So pretty cool stuff. I don't know all the history. Sorry if I said something wrong, but I know they're involved in all of this. So let's now write this. So fundamental theorem calculus part 1. A very long name, abbreviated as FTC1. Much better name, FTC1, instead of Fundamental Theorem of Calculus Part 1. So FTC1 says exactly what we had. This is just a little more formal way of saying it, is this. If f is continuous on AB. Remember, we needed continuity to be able to have integrability, meaning we can actually find the area underneath the curve. Then the function G defined by so the x's that we're allowing are between A and B, right? We can't go past, we can't stick a number larger than B into here because we don't have a notion of what that is. So for this guy, so this function G is now continuous, is continuous as well, is continuous and differentiable actually. And it has that property, continuous, there's small, continuous on AB and differentiable so you have continuity at the points A and B guaranteed as well, but differentiability is not guaranteed at the endpoints. This is the small difference. And last but not least, the big part, I'll write in a different color, and G prime of x is f of x. That's the key takeaway. So fundamental theorem, calculus part 1, aka FTC1. So let's break this down one more time. So we have a continuous function on this interval, and then if we define this new function that, like we saw an example of this, in this way, then this new function is going to also be continuous on A to B and differentiable everywhere too, except for maybe at the boundary points. And the key property is that its derivative will be equal to just the value of the function, which is pretty crazy. So the slope of the tangent line of this function, which this function is giving you areas, right? So it's saying the rate of change of area is basically getting canceled out. When you take the rate of change of the area, you just get back the original function. And we've kind of seen this already as well. Okay, now in terms of a proof, in an ideal world we would do this, but we're going to skip it because it's probably will detract from your understanding of what it's saying. And later, if we have time, we might come back and prove it because it's an amazing, amazing, amazing result. And these fundamental theorem of calculus proofs, the part 1 and part 2, which we'll get to, they use these weird theorems like the mean value theorem that you were probably like, why the heck are we learning this in Calc 1? That theorem comes in much need in the proof of this. So the mean value theorem is a very important theorem. It just may not seem like it because you don't ever use it to prove this big result. So again, none of this stuff is just made up to torture you. There's a reason for it. Okay, and then maybe let's see an example. That would be part 1. So FTC1 example. Okay, so suppose you define this function g of x. It's a very bad g. G of x is the integral from 0 to x of this guy. And then somebody asks you to find the derivative of g of x. Well, what is that? Well, according to the fundamental theorem of calculus, this is the same as g prime of x. That's what we saw in the statement. That's just this function. It replaced with x's instead of t's. Right? This is f of t, but we wrote it as f of x. So you literally just replace the t's with an x. That's it. So easy as that. And again, this seems like, okay, what the heck? Why do you care? We'll see. And definitely in your other courses, you will see where this comes in handy. Okay. And now, I gotta erase all this to probably set the other one up. We'll talk about the second fundamental theorem of calculus, which, again, we saw already that it works with our examples, but let's state it in like full detail with all the assumptions needed and things like that. So I'm just going to write FTC2. Fundamental theorem of calculus part 2. It says this. So if f is continuous, again, you need this to guarantee that you can find the area underneath the curve. Then it says the area underneath the curve from A to B is just this. And then again, what was capital F? Remember, capital F is an antiderivative. And then, what does that mean? What does it mean to be an antiderivative of F? It meant this. It meant that if you take the derivative, you get back this guy. So f prime of x is this. So let me give you an example of this. So, if you had x squared, there are an infinite amount of antiderivatives of this function. In general, one antiderivative could be x cubed, let me write it as 1/3 plus 1. Or another one could be, let me say, f sub 1 and f sub 2, so two different antiderivatives. Right? In general, we wrote plus c, but here are two concrete things. What c can be. Now, if you take the derivative of either one of these, you will get back x squared, right? If you use the power rule here, the 3 hits this, it goes away, and this becomes an x squared, plus the derivative of this is 0. So the derivative of this is x squared, and this one as well. So see, f prime, the derivative of capital F is the original function, small f. That's what it meant to be an antiderivative. So it's saying for any antiderivative, this will work. But in general, what you can do to save you some hassle is just to consider the easiest antiderivative, where you just don't add anything, where the constant is 0. So just like 1/3 x cubed. That's probably the easiest one, just to save you, annoying computations. I mean, the constant ends up canceling out anyways, so it doesn't matter. But, right, do you know what I mean by that? Because if f of x is, some other function, let's just say 1/3 x cubed plus c, then f of b is 1/3 b cubed plus c, and then f of a is 1/3 a cubed plus c. Now what happens when you subtract these? Well, this becomes 1/3 b cubed plus c minus 1/3 a cubed plus c. And then when you distribute the minus sign, you get minus 1/3 a cubed. And then you get plus c minus c. So see, the constant just cancels out. And so you're just left with this again. So again, the constant doesn't matter, so you might as well just take it to be 0, or just to save you some hassle and of time and stuff like that. So hopefully that helped kind of clear that up. And we'll definitely talk about the antiderivative rules and things like that, because it's probably been a while since you've seen it. Of course, you guys can ask me questions in class during the Zoom meetings at any time. But the amazing thing about this result says that you only need to stick 2 numbers into a function. That's it, and subtract them to get the area under the curve. So as opposed to, oh my gosh, coming up with this curve and then making these rectangles and then finding the limit of the area of these rectangles and blah blah blah, instead of doing all of this work, all you have to do is take the antiderivative of this and stick 2 numbers into it and then subtract it, and that gives you the area. That perfectly gives you the area underneath the curve. So this is also an amazing result. It's very powerful. So very, very good. It's kind of like, when you use the limit definition of the derivative as opposed to just, using the rules. One takes forever, the other one is immediate. Okay, so now let's do an example of this, where we use this guy. So let's find this. So again, what is this asking us? Well, we have the function x cubed. It will look like this. So at -2, it's down at -8. At -1, it's at -1. Then at 1, that's at +1. So the function looks like this, and we're interested in getting the area, the net area, basically. So we want this area, the net area. Now normally we would have to use, the Riemann sums or whatever, and huge pain in the butt, but if you remember, now might be a good time to refresh on some of the antiderivative stuff. Is, the antiderivative has this property, right? Capital F equals small f. So we want to come up with a function whose derivative will give us x cubed back. So if you think about it, if we have this x cubed here, when you take a derivative, the power rule, the derivative of this guy gives you 3x squared. So you lose a power here, okay? Meaning the function whose derivative we want to take, because we want to get a cubed here, right? This should at least have a 4 here, okay? So if we do that, then we get 4x cubed. Okay, that's really close. We just wanted x cubed. So how do we fix this? Well, you just multiply this guy by 1/4, right? If you multiply this by 1/4, now what would happen is you would still bring the 4 down, but now it's getting multiplied by 1/4. And so then you get just x cubed out of this. So, if you do say f of x, capital F, is 1/4 x to the 4th, then its derivative is really x cubed. And so it's satisfying this property. And so that's why it's the antiderivative. So in general, I know we can make this, we can say this. The antiderivative or I'll still use A, the antiderivative, because we haven't talked about the indefinite integral. We'll get to that in the next section. The antiderivative of a power is just going to be this, which in our case, n was 3, right? So 3 plus 1, that's the 1/4. X to the 3 plus 1, that's x to the 4th. There's one caveat, is n cannot be -1, or else we'll be dividing by 0. And we'll talk about the extremely, extremely important scenario when n is -1 later. But for now, this is what we have. So back to what we were doing. Sorry to get sidetracked. So we know by the fundamental theorem of calculus 2, or sorry, just FTC 2, that this is going to be 1/4 x to the 4th. And then here's some new notation that maybe or you have seen or not, but we're going to put this vertical bar here and write -2 and 1. What does this mean? Well, this means stick this guy into your function and subtract it from when you stick this guy into the function. So this will literally equal 1/4 1 to the 4th minus 1/4 -2 to the 4th, which is exactly the form in the fundamental theorem of calculus. This is capital, this is f of b, where b in this case is 1, minus f of a, where a is -2. But this symbol right here is really nice because, and you read it as evaluated from -2 to 1. It's a nice shorthand way to write some of this stuff. So evaluated from -2 to 1. Okay. So that notation is super, super nice. And so what does this give us? This gives us a 4th minus 2 to the 4th is 16 divided by 4 is 4. And so this gives us -15 over 4. Yes. So that gives us -15 over 4. And so that you can see without any Riemann sums, without any difficulty, we can perfectly figure out the area underneath the curve, or the net area. So that's really, really, really powerful result. And that's why it's called the fundamental theorem of calculus, you know. It's an extremely useful result. Okay, let me make sure that we're not missing anything. Okay, I think this is a nice natural stopping point because we've talked about what we need to, but definitely we will practice this process a lot because it's going to be very important. And what we're going to do is next see, you know, how the process of integration applies to certain geometrical things like finding volumes and areas like that. And next we'll figure out how to take the antiderivative of some tricky things that are hard to do at first, but that's to come. But for now, thank you guys. I'll see you next time.